Okay, so we're going to do an example of showing that a function sequence converges uniformly on a given set. Here my function sequence is x squared divided by n, and the set of interest, capital A, is the closed interval 0 to 2. Now, if you're asked to show something converges uniformly, the first thing you're going to have to know is what it converges to. Well, that is until we get to the Cauchy criterion. But for now, we need to know the limit function in order to figure out whether we converge to it uniformly. So my claim is that the limit function excuse me, is actually the constant function 0. And that actually makes sense because as soon as I fix an x that's between 0 and 2, and then I let n run off to infinity, right, anything divided by something that goes to infinity is going to be 0. So that's my limit function. And so now I want to show that the convergence to that function really is uniform. So let's let epsilon be bigger than 0 and consider fn of x minus f of x. That's the thing that we want to make small. And for this particular example, that's x squared over n minus 0, which is the same as x squared over n. So if I use the fact now that x has to live in the interval 0 to 2, that allows me to get a bound on this term that now doesn't depend on x, right? I can't choose an n that depends on x. So I want to know how large can this thing be on my set. And the largest it can be is if x is 2. So this is less than or equal to 4 over n, since x has to be between 0 and 2. And now we want that to be less than epsilon. So if you move the n over and the epsilon over, this will happen if we take n sub epsilon to be bigger than 4 over epsilon. And then we sort of finish this up the same way we would many of our other proofs. Let epsilon bigger than 0, and take n sub epsilon, something bigger than 4 over epsilon. And if n is bigger than n sub epsilon, we have that the difference in our function sequence and our limit function, which I've already shown is x squared over n, that's less than 4 over n, which is less than epsilon for all x in the interval 0, 2. And that, in fact, is the definition of uniform convergence. We found one capital N for each epsilon that works for every x in the set at once, so every x between 0 and 2. And by works, we mean can make the difference in the function values less than epsilon over that whole set.